Good evening and welcome from Maine. This is the ninth and final lecture on the 1.2 billion years of geology in Maine in the New England area. The original series was 10 videos. Some of them got broken apart into A and B, um, and I kind of looked at the last section, which is the Cenozoic, which I believe I broke up into two parts, but I'm just going to go through it and do it all at once and get it done because I want to start working on some other things. And full disclosure, when I went back and watched the original video of this section, I just caught numerous mistakes that I made and just said some wrong things. Not necessarily big things, but just small errors here and there, more so than the rest of the lectures in the series. And really, the actual reason behind it all is because I would say that I probably know the least about the Cenozoic, and definitely at that time. Well, it's been almost a year now, and I have been diligently researching, and I've come, a long way since then. So I think that when I do that this time, it will be a lot more thorough and more accurate. And I really say and get across some of the points that I really want to drive. The Cenozoic era, this is the end of the dinosaurs, the rise of the mammals. We're starting out at 65 million years. We're going to take it to the present, and then we're even going to look into the future at some slides just to have an idea of what we think is going to happen in the next 250 million years when the Atlantic Ocean decides to shut, if it so chooses to do, and we think it will. It's done this before. It's done this numerous times, so why wouldn't it do it again? In any case, here we go. Anyway, Cenozoic is 65 million years to present. It's known as the age of mammals. Anybody watching this that can understand language is a mammal and a human being, and this is the era that really brought us into fruition. So anyway, the Cenozoic is the current geologic era on Earth, beginning at 66 million years ago and continuing to the present day. It's the most recent of the three geologic eras in the Phanerozoic eon and is known as the Age of Mammals. The name Cenozoic means recent life or new life because the plants and animals of this era are most similar to those living today. Here are some characteristics of the Cenozoic era. A. Mammals. Mammals become prominent after the extinction of the giant reptiles. Examples of Cenozoic mammals include the woolly mammoth, early horses, cat-like carnivores. Birds. Birds became more prominent after the extinction of the giant reptiles, and I'll show you some. You're actually shown some pictures of it. I'll rehash those again. Marine mammals. Marine mammals took over the large marine life niche, replacing the marine reptiles. Whales evolved from carnivorous land animals, and this is very true. When you go out to Africa, especially, I believe, the Sahara. Is it Sahara? I always mix my deserts up. In any case, when you go out to the deserts in Africa, especially northern Africa, there's just areas where seas dried up in the Cenozoic, and we find all sorts of whales that were just stranded and died. It's quite sad actually that you find areas and there's just whale graveyards randomly placed. Well, they're not random. They're just they're old seas that were dying up and drying as the Sahara became drier over time. Just going back 20,000 years ago, fairly sure that the the large desert area of northern Africa was mostly a savanna. And then prior to that, we know it was wet at one time. We know that it was lush and everything like that. And we also know that parts of it were occupied by epiperic seas. So that, having said that, as the mammals that would become the whales and the dolphins, etc., began to evolve, you witness the more or less the more primitive versions of these, and when we look at the more primitive versions of these, the whales, especially the whales and dolphins, we watch a couple of things happen. One, the what was once limbs they go into flippers, um, and the tail becomes well, the tail remains a tail, but it develops a sort of a wide end of it so it can propel itself. And more importantly, and this is the really crazy part, is we watch the the blowhole, which is where the whale breathes, migrate from the snout up to the top of the head. So big clue right there that, if you're watching the air duct go up to the top, well, that's the part where the whale breathes the easiest, and so it makes sense. As these see, I've always said that the dolphins and the whales are more evolved because they made it back to the water. We came out, we're on land. They came out, they were on land, and early whales really looked like the most terrifying bears you could imagine. They had a much bigger jaw. And they were definitely a force to be reckoned with. They were very gnarly, aggressive. Some were carnivorous, obviously. Others were not, because we have both whales that are carnivorous and then ones that are, well, some are filter feeders and some are, they eat other whales or they eat meat. I guess would be a better description, because planktons can sometimes be animals and sometimes they're not. Sometimes they're plant materials. But anyways, the point is that the whales went through a evolutionary, almost I don't want to say drawback, because it's not a drawback. They just came out of the water and then went back in, and we can record that in some of the fossils that we see, especially in the African continent. Climate. The climate was much warmer and more uniform than today during the Paleocene epoch. That's right after the extinction of the dinosaurs. Oceanic circulation began to be global. Once Pangea broke up, we started to have the ocean be able to do a circumnavigation around the planet, and so that helped also regulate temperatures better. It also allowed the waters to mix and cold water to be created, cold water to travel along the bottom of the oceans, which is very important in stabilizing our climate. And it also allowed carbon to move around and the carbon sink to become more active and hold more carbon. So a lot of things happened that went in our favor to stabilize the climate and basically the Earth after the massive KT extinction event. Changes in circulation helped lead to the development of glacial episodes in the late Tertiary and the Quaternary. We know that in the last 2 or 3 million years, we've had many episodes of glaciation, and that's because the climate has continually cooled since the Cretaceous. The tectonic activity, at least in the Cenozoic for us, well, at least in the United States, is in the West Coast. The East Coast has been relatively quiet, passive margin. The Appalachians have steadily eroded. The Canadian Shield, the eastern part of it, steadily eroded and got scraped by glaciers. The Mediterranean Sea, or the Tethys Sea, rather, closed up, and what's left of it is like the Caspian Sea, possibly part of the Aral, which is now pretty much dried up, and the Mediterranean. That's what's left of the Tethys Sea. Europe was essentially a passive margin. Africa more or less dried out. Africa also started to rift in the eastern part of it. We have the large rift zone of East Africa, the Red Sea development, pushing Saudi Arabia north and then rotating it counterclockwise to create the Red Sea. India slammed into Asia and created the Himalayan mountains. And then, of course, the Pacific Ocean developed all sorts of subduction zones on the northwest, the west, the north, and along the eastern coast too. So you have almost a complete circular area of subduction that's going on with the Pacific Ocean. The Pacific Ocean is essentially surrounded by subduction zones. So, one should think that the Pacific Ocean is getting smaller, and I believe it is. And of course, in California with the San Andreas Fault system, evolved from subduction along the western margin of the United States. Of course, the Rockies were built in the late Cretaceous and around 40 million years ago stopped. And now because of the subduction um, of the Eastern Pacific Rift Zone, I'm trying to think of the name of it. Can't think of it. But anyways, it's part of it's off of right now. It got subducted under Oregon and Washington and Northern California, which is why the Cascades are there. And it's also it's offshore once you go down past Baja, California. But it's basically rifting off Baja and splitting that area in Southern California off of North America, and eventually that a slice of California will eventually be separated from North America, and it will move northward. And I believe it goes like that. Yeah, it'll eventually move northward and then smash into Alaska. So, anyways, that's the Cenozoic. Temperature over the last 500 million years. People are probably sick of this, but it's a simple map, and it just really shows, the basics that I'm trying to tell. The peak of the Permian when the extinction event happened. Obviously, we had some very high peaks back in the early Paleozoic, and we have some very steep drops. They're usually associated with extinction events. Anything below this line is the Earth with polar caps, and of course, we know that Gondwana had massive glaciers from about 350 to about 275 million years ago. And then, of course, they melted, and then temperatures rose. And most importantly, here is the KT extinction event, the dinosaurs, and we have just massive fluctuations from it, due to the impact and, of course, the volcanism associated with the Deccan traps. But then temperatures plunge, and they have been doing so for pretty much most of the Cenozoic, and we are now down in some very cold temperatures where we are today, and that's why we see glaciers. We're partially glaciated. We have glacial caps on Greenland, and of course the entire continent of Antarctica is completely glaciated by under about 2 kilometers of ice. So anything above, there's no glaciers. Anything below, and as you can see, we are clearly down here in the Earth with polar cap zone. As I said, and I just love this beautiful picture of an artist's rendition of what the terror birds look like, right after the KT extinction event. You gave the Earth, 8 or 10 million years or so for things to, for everybody to get their bearings, and of course, due to the ferns that come up immediately after some sort of a forest fire, or just whenever a landscape just gets absolutely destroyed, the ferns are the ones that come up first. Just so happens that the birds that eat ferns that don't fly were the ones that first prospered and grew to enormous proportions, as you can see here. This is a terror bird fighting some sort of a saber tooth. Not all of these, I believe, were carnivorous. Some were, some weren't. They may not have been quite as gnarly as this. Maybe they were worse. I don't know, but they definitely existed because we have proof right here. This is about the same size. Well, the Tyrannosaurus skull would be a little bit more robust, but for a smaller Tyrannosaur, it's about the same size. And this is a direct descendant of the Tyrannosaurs. The terror birds, carnivorous dinosaurs went and became birds. And this is one of the first ones that developed. And as you can see, the jaw was about the same size, if you think about it. The skull was about 4 feet. Well, this one's probably about 2.5 feet long. The Tyrannosaur is about 4. And you will have a very robust beak right here. The teeth are now gone, but it's replaced with a very nasty weapon right here, which, the tooth of a Tyrannosaur is about this big. This is probably much stronger than an individual tooth, I'm guessing, because otherwise, Tyrannosaurus teeth broke all the time. Nothing is breaking this. So it's the new and improved version. So let's just talk about the evolution of mammals, because the mammals are the ones that are going to now take the throne. And as we discussed way back in the day, we start down here with a common ancestor that basically evolved from an amphibian. We end up having the amniota, which is basically saying that instead of laying eggs in waters like the amphibian, something came along and decided, yes, we can make an egg, and the egg will have a shell, and the egg will grow inside the organism, and then the egg will be laid and either kept warm. Yeah, actually, they're always kept warm because both birds and reptiles, they either bury them or they sit on them, and then it will finally hatch. And it eliminated the need to have to always keep your layer. The only way that the amphibians could reproduce is they needed water. Well, the reptiles solved that problem. So the reptiles and the mammals split right here in the Carboniferous, in a sense. So one goes to become the true reptile. The other, these are like pre-mammals. They go on to become mammals. And as I said, one of the things that's very very well known about mammals, obviously, is that we are warm-blooded. And if you think about it, this guy right here, and I had a discussion on this a few lectures back, that this is a relative of ours, one of the earlier ones, and what you can see is that this thing had this big fin on the back. Now, there's all sorts of theories on what this was for. Mine is that it was used to regulate temperature. I think it was its primary purpose. It may have been done for display, for mating, but it, at noontime with the sun directly overhead, it doesn't need to be used for heat. However, in the morning and the evening, when it gets cold at night, before it sets, you want to warm up, and in the morning after a cold night, you want to warm up. And so having this straight up, the sun's going to hit it at an angle for the early and the evening hours, where it's going to be able to absorb as much heat as it possibly can and drive its metabolism. So that's my idea on that. It's my theory. I'm sticking to it. So you go to here. This is another, basically another version, an early mammalian reptile, and this guy went extinct. I don't really know much about this, but so we go here. This is the path of humans, by the way. We go here, and then you have a Therapsida. This is sort of starting to turn into more of a almost like a cat or a dog sort of form. It's a low walking reptile, but it's starting to look more and more almost mammalian. And then we go up to here to Cynodontia, and these are more or less the we're getting into things that are more like gorgonopsids and stuff, what have you. And this is the peak. This is a mammalian peak right here, where you've got something that's about we'll say gorgonopsid was probably bigger, probably up to 6 or 8 meters. So yeah, they were big. They were very much like larger than a lion, more like a bear. You had the saber teeth developing here, and this guy was the apex predator of the Permian, and this is where evolution basically peaked in the Paleozoic. And then we had the huge extinction. We cross the border, and we start. The mammals become small again. In other words, we were small here. We started getting big in size, and then we got enormous in size, and then we got whacked, and then we started out kind of small again. And the mammals remain small and relatively sparse through the Mesozoic, because that's the time of the dinosaurs. And then we push through another extinction event, and we have mammals that we know today. And it's funny because the monotreme, this is a platypus. Marsupials are pouches. And of course, we are placenta mammals. These are all mammals, but one is a monotreme. The monotreme lays eggs. The marsupial has a pouch, and then the mammals carry the young in their body until they are born. Basically, they're born without a shell. They are grown within the body. So if you think about it, the monotreme, basically like the platypus, is a derivative of something that was around in the Jurassic, and it makes sense. We were still probably laying eggs at this time. When we evolve further, we end up moving to a point where we are no longer laying eggs, but we are actually giving birth to very, very small offspring. like very underdeveloped, but yet that underdeveloped offspring makes the trek out of the body of the mother, and yet finds its way to the pouch. How it does it, I don't know, but it does it, and it's very effective. And so we have the marsupials, and the marsupials are found only in Antarctica and Tasmania, and the reason why is because the Lombok Strait between Bali and Lombok is so deep that no ice age was ever able to lower the water enough to have a land crossing. And that strait itself, the current is just so nasty and so treacherous. You have standing waves that are in the order of, 6 to 8 feet high sometimes tens of feet high. Nothing is getting across that. It can't swim it. And so since mammals don't really, land mammals can't swim, generally huge distances, you're not going to make it across. So the marsupials were all over. At one point, the marsupials came out of the Cretaceous, and they were all over probably most of the world. But for one reason or another, the placental mammals were much more effective, and they basically caused the extinction everywhere on Earth except for the Australia and Tasmanian area. And again, because these guys can't get across, whether or not we actually got across early on, I don't know. But the marsupials thrive, and they're still there today. The placental mammals, we got our basic kick in the late Cretaceous, and we have been going gangbusters ever since. So at this point, it seems as if the growing your young inside your body in a protected environment and giving birth to a live, fully developed young seems to be the way to go. Because we are now the dominant species. We're not the most populous, probably that goes to the insects, but we are definitely, this seems to be the thing that works in today's planet. So that's the evolution of the mammals. And if you want to get crazy with it, you can look at, go and look at charts like this and just absolutely make your mind bend and go crazy. But this is the lineage of mammals. I don't know if every mammal is listed on here, but I'm not even going to go through it because it's just too. Let's just track man though. Okay, so here's man. We are a we are a hominid. And we are Homo sapien. We have had numerous species that of man that were not. We are Homo sapiens, yes. We've had Homo habilis. We've had Homo erectus. We've had Australopithecus. So we've had different versions of the Homo sapien. For instance, we had Homo sapien neanderthalis, Homo sapien Cro-Magnon. And then we are Homo sapien sapien, that's us. So we can go back and we can just crawl our way back, and you go here, and then you go to here, and then 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 there's a break in here somewhere. They don't know what the time distance is, probably very large. But anyway, this is our group of mammals. We are primates. You want to find a cat, you go down here, I believe, to carnivora. I believe a cat is the only true, yeah, right there. Yeah, these are cats, these are horses, these are hoofed, rather. You got the camel, and then you go down to, the whale and what have you. And if you go here, kind of interesting, you've got, I think that's manatees up here, which are related to elephants. You've got your rodents, kangaroo, those are placentals. But yeah, you've got, basically everything listed out here in a very complex, crazy chart. And again, if you would ever want to, make yourself, really challenge yourself, try to understand, how this all came to be. But it all comes down to a common ancestor if you go back far enough. And that common ancestor was a reptile, and before that it was an amphibian, and before that it was a fish, and so forth. So, hooray for evolution. So, Paleocene, 60 million years ago. This is kind of what North America looked like. What we see here, we've got, Caribbean stuff going on here, probably Puerto Rico. You've got some seduction. I don't think that this was advanced at this point. This was probably back here somewhere. You have a Gulf of Mexico. You have Florida here, more or less. This is after after everything just the Atlantic Ocean is on its way to being a very large ocean. The East Coast is So Paleocene time, we got a lot of rifting that's probably mellowed out now. The mountains had probably been worn down to a more or less a highland. Um, on the west coast, we have trenches and we have accretion of the building of the ancestral Rocky Mountains. Um, Greenland has rifted off of North America in a Oligocene that will eventually fail as the Icelandic hotspot moves underneath Greenland and over here, and then this area here begins to open up. You have the Arctic Ocean here, which is really more or less an extension of the North Atlantic. Paleocene, paleogeography, so that's hard to say. Again, you have, it says mountainous here, but this is more or less probably a high rolling land, a tableland of rolling, probably some mountains, but they're mostly rounded and rolling. They're not sharp peaks anymore. You've got shallow marine sediments being dumped into here, right in here and here. The Gulf of Mexico, the shoreline's probably back here somewhere. You have what's left of an empiric sea that's drying up in the Cretaceous. And you have a trench back here, so these are deep water sediments. And of course, you have lowlands here where a lot of these are being eroded out. And of course, you have the Rocky Mountains in their full swing right here, probably approaching well over 20,000 feet at this point. Eocene period. 50.2 million years ago, or just say 50 million years ago. Here we are right here. The Atlantic, we're starting to look a lot like, what we see today. We still have a fairly high sea level. The Gulf of Mexico shoreline is much further inland. The Mississippi is not filled out its deltas yet. You have South America further down here. It's kind of moving upwards in a northwesterly direction, more or less, and it will kind of come up to this point right here, and you have the Caribbean Sea. It's much bigger at this point, and this may or may not be connected. I'm not sure when the actual isthmus of Central America was created, but I know it's coming very soon because we have a subduction zone off of here. Africa is a little slightly inundated, and that makes sense because when this split right here, this probably had somewhat of a deep valley area right here, and again, sea level's higher. You can see that Europe and part of Western Asia is flooded. The Mediterranean is getting smaller. The Tethys is closing. The Indian Ocean is growing. This is the Indian Ocean. And India is racing towards Southeast Asia and is going to create the Himalayas. It's a gigantic mountain range. And Antarctica and Australia have parted ways. Eocene 40 million years ago. Rifting has stopped here and has now started to go over here and open up the true North Atlantic. We are still in a fairly flat highland here. Not much going on the East Coast. The coastline of the Gulf of Mexico is starting to look more familiar. Sea level is still slightly higher. It's inundating a couple of areas, and of course the Florida Panhandle is still underwater. This should be over here somewhere. These are probably back here, and they're slowly getting dragged along as this subduction zone continues to pull this area right here this way. And it's actually going to start pulling Pacific crust under and out this way. So I've been asked a lot of questions about this next part, and this next part is where I really struggle with because it's nobody knows. That's the problem. This isn't the ideal slide I want to use to start this, and I'm going to go into much more detail in it in a little bit. But this gives you a basic idea. There's a few, this has to do with Appalachian uplift around 30 million. In theory, the Appalachians should be flat as pancakes. They should like the Great Plains, but they don't. They're almost a mile, they're over a mile high in some places. We see the roots and the cores of very large, deep mountain ranges that were there at one time. So the question is, they should be, those cores and roots, they shouldn't be as high as they are. Now, granted, if you have a mountain range that has a really resistant core, of course it's going to show up eventually, but not at the height that it is. So we have a couple of theories, and I'm going to just kind of go into three, but I'm just going to hit this first one right now and describe the other ones in more detail in a bit. And I'll also just describe this one. So this is the Adirondack Mountains. We know, or we think something is going on under here, and the idea of a plume. And we, through seismic records and geophysics, we know that there's something warm underneath that's doming the Adirondacks, okay, as represented here. However, there's a lot more to this than probably just that. There may be, in fact, an area of magma underneath the Appalachian Mountains trending northeast southwest that is also heating up, and that it might be because of decompressional melting associated with the deep crustal root of these mountains, that you've taken off 6 miles of materials here now, and it's spread out here and it's spread out here, so it's actually pressing down here and pressing down here, more on this side. But as that root got pushed very deep, and over time, as it comes up, the root stays hot, but then without the pressure, it begins to melt periodically, and you get upwellings of magma, and as you do, it has a tendency to push up the crust around it. Whether or not that is exactly what's going on under here, we do not know yet. But I do know that under the Adirondacks, it's pretty clear that there is something a little bit more aggressive under here. So I just wanted to give you an idea of where we're going to go with this. There's also another idea that we know that a huge slab of the Iapetus Ocean went underneath North America, and eventually when that slab gets down to a certain depth, pieces break off and they melt and they get recycled. Now you have to imagine the whole weight of an oceanic crust being under has a lot of weight. It's not something that's light, and it's very dense, and it has a tendency to pull the crust down with it. Now when that thing breaks, it's going to go down and it's going to start to heat up, and it's also going to allow magma that's here and here to start moving through. In other words, what was here could not get here because this was in the way. This is now getting here. This is finding voids, or not voids, but an area that's not being held down quite as firmly. And again, you get melting, and sometimes this will melt because it has water in it, and so the melting temperature goes down, and you generate plumes, and they get enlarged in here. And of course, when this weight is taken off, this thing bows up, and that could be another reason. We have slab break off under here, possibly. And then the third thing is that you take all the weight that you had on a huge mountain range that was here, and you put it here, and you put it here. It presses down here, and then of course there's no weight here, and just by the fact that there's not nearly as much weight as there once was, this will have a tendency to rise. So probably what's going on in the Appalachians is maybe a combination of all three, and I'll get into that in a little bit. So anyways, just hold that thought, and we'll get into that in a bit. To further enhance what I was just saying about this, when you see this right here is likely, possibly represented by something like this. What this line right here is, this is North America, this is accreted terrains. They have different densities. The North American craton is old, cold, and very dense. The accreted terrains were volcanic. They traveled across, they were rifted off of Africa and South America, and they are not nearly as dense, and so they have a tendency to float higher up on the mantle, as you can see here. This is where the cold, basically the solid crust, meets the moho, or basically the mantle. And what you're seeing here is that right here is represented by this, and then this crust here is represented. So you have a very steep drop off right here, almost in the order of 15 kilometers difference. And so the idea is that this area here underneath is much warmer than this area here, at least at this particular depth. This area does get warmth, but it's much deeper. So this is almost kind of showing us that maybe this suture line right here, there's part of deep down, this part of the moho rode up and over this part at 20 kilometers or so. So what we're really trying to explain here is that what's underneath this crust is a hell of a lot more warm, a hell of a lot more less dense than what's under here. And because of that, this area may have bowed up a little bit quicker than it did over here, and may not have done anything. But we do know that at depth, we have essentially a very steep drop in the moho layers by almost 20 kilometers, and that's very significant. So, and that's represented by this right here, and this is accreted terrains. This is North America, and this is the line called the suture zone, the Iaponian suture. This is where the ocean closed, and basically parts of Gondwana got slammed in and adhered to this, and that's the difference. So right here, 30 kilometers, 35, 40, so 10 kilometers difference right in here. In 10 kilometers, and in this short area, the depth from moho goes from 30 to 40 kilometers. So there's 10 kilometers difference right in here. And these are the terrains. And this line right here is this line right here. Anything in blue is the old Laurentian crust. Anything on this side of it, basically green, yellows, purples, whatever, these are what we call foreign zones or exotic terrains. And these were like this area right here in Gandaria. That is part of an island arcs, and basically volcanic sediments from island arcs associated with the Gandaria terrain. This right here is one of the island arcs that was welded onto, accreted onto North America during the tectonic orogeny, as well as this one here. So you have tectonic orogeny, you have the Akkadian orogeny, and then of course, you have Avalonia right here. But this line right here is basically the same line as this, and this is where the Iapetus Ocean basically made its last stand, and this is the suture zone right here. Anything over here is North America native, anything over here is from very far away. And again, anything over here has the moho is much shallower than it is over here. And here is another, this is sort of to get the idea of what slab breakoff was when I was just talking about. This is not North America. This is really from the Mediterranean, but the idea is still the same. So this is Africa coming north, going underneath the Aegean terrain. But for our purposes, let's just don't even think about the names. Just realize that this is going under, and as it goes under, this will bow up, and then the slab begins to shallow right in here because it's meeting resistance, and it's almost, so it's dropping, and then it's basically being forced up this way, and as it does, it eventually will snap. This will come under and start going underneath. This will snap right here. So this is the first thrust fault, and then the thrust fault is right here, and then the thrust fault will begin to move back, because once it gets to a certain point, it begins to form another thrust fault behind, and then you get a void right here, and then a new thrust fault forms right here, and what happens is this ends up becoming thinner and thinner, and then eventually it snaps. And when it snaps, this all goes down, and this thing will rebound. And so this is essentially, so you have a thrust, then you have a new thrust that forms behind it, and then you have basically a shear zone where things are running by each other, and you have a new mega thrust that ends up forming, and then you have stretching, and then eventually as this dives further and further and this stretches out, this thing will snap. Now, this is not exactly what happened underneath North America, but this is kind of how it works. So take it with a grain of salt. Oligocene, 25 million years ago. Again, now the Appalachians have begun to lift a little bit because of this, or a combination of this with some other things. And with the Appalachians lifting, you're starting to get more erosion, and you're starting to get sharper peaks again. Here is Ogunquit again in the Marginal Way, our beloved Marginal Way, right along the coast right here. Probably looking very much like, I don't know, probably not much different than today, to be honest. Maybe a little bit warmer. But you've got some rolling hills. You do not have the sharp peaks of the White Mountains, because unless there's been a recent glaciation, you wouldn't have it. It would be more rolling, more like Mount Mitchell down in North Carolina. Gulf of Mexico, Florida is starting to take shape. Cuba, think this is Haiti. Yeah. And then this is, of course, the Puerto Rican, this is Puerto Rico, and then the subduction zone right here, still dragging everything this way. Miocene, 15 million years ago, we had a little bump up in sea level, so you've got some flooding on the Piedmont here of the eastern United States. The Mississippi Delta is pushing itself now out into the Gulf of Mexico. You've got the Gulf of Mexico looking as it does today. You got Cuba, the Haiti, all that down here, Yucatan, and of course the Puerto Rico, and of course the trench right here, dragging everything off. Miocene period global view. The global view, again, sea level slightly higher. You can still see some flooding right here. This is what's left of the Tethys. India has slammed into Southeast Asia. We've got a giant plateau that's been pushed up from the subducting from the ocean crust that was on the northern side of India as it traveled across the Tethys and then slammed in. You've got the world's biggest mountain range now. Australia is moving into its present position. The Indonesian arc is right here. You have arcs and trenches developing in the Western Pacific. You have the Puerto Rico Trench Zone right here. And of course, you have the huge Eastern Pacific subduction zone going out of North and South America. 8 million years ago, not much different from today. Baja's split rifting off. You've got the islands off of Southern California that are much closer but are being pushed out. The Gulf of Mexico is looking like it does today. Florida Panhandle is finally coming out of the water. A strike slip fault is here. It is now pulling crust. This crust was once here. These two were side by side, but now it's getting pulled along this subduction zone, and this is going to just continue to keep going. And Puerto Rico's right here, Yucatan right here, Ogunquit right here. Again, 8 million years ago, probably rolling hills. I just don't know enough about the glaciations past 5 million years ago, or 2.5 million years ago. I know there's more. I just don't know them that well. So, and I haven't seen any ice show up here, so I'm assuming that this is probably a rolling hills. You have Greenland, you have the North Atlantic, the hotspot Iceland is formed here. I think that's a bunch of islands off of England right here. I forget, they're associated with the hots. Like these were actually connected to this, and then that when the mid-ocean ridge opened up, it pulled pieces off, and so they're much older than what Iceland is. But these are, I believe this is volcanic massive right here. Big bunch of flood basalts, kind of like Iceland. And of course the Arctic Ocean, you have the Aleutians here, Kamchatka here, Bering Sea, and it's, the Earth is really starting to look like it does today. Pleistocene, 1.2 million years ago. This is the extent of the last ice age, one of the biggest ones to come down, basically cover North America down to a latitude of Virginia. Rocky Mountains are absolutely loaded with snow. I have a hard time believing that I think this goes more like this, the snow cover, but the glacier wouldn't move through here because the Rocky Mountains are too high. So you would just have localized, just piles and piles of snow, in the order of thousands of feet deep. But oddly enough, we don't see much glaciation down in this area. So if anything was flowing, it didn't really flow much. I wouldn't be surprised if somehow you couldn't find some sort of lobes in here, but I don't know. It's just me thinking. The strike slip fault is really pulling crust with it this way. Puerto Rico's here. It's this all started back here and it's been pulled this way. Pacific crust right here is now being pulled and stretched as this progresses to the east. And Ogunquit's buried under about a mile of ice. Glaciation. So this is a superficial geologic map of Maine. We use bedrock and superficial maps, and a superficial map is basically what you'd see under your feet if you're standing there. So this essentially has mostly glacial features. So in other words, muds, sands, deltas. I don't know what this is because I can't blow this up. But around the Baxter State Park area, you've got this formation here, which I'm going to probably see in more detail. But this is the extent right here that the ocean ended up flooding about 10,000 years ago. Once the glaciers pulled back and released all their water, the state of Maine was depressed down about 200 or 300 feet. And because of that, and because there was a lot of water being pumped into the ocean, sea levels inundated Maine up to this sort of this line right here. So anything in this area is what we call marine muds, and you find marine deposits all through this area right here. And then once you get past the zone, you don't see any of that marine mud anymore. In other words, the silt and stuff that's deposited in the ocean collects on the bottom, and it makes a layer that you see all the way through here. But once you get past it, you don't see it. So you know that this area back here was never inundated. So I'm not going to go into this map in great detail right now because I'm going to talk about glacial stuff a little bit later in the lecture. Mount Katahdin's official geologic map. These would be sort of what you'd find in a recently glaciated area, and Mount Katahdin is no exception. The pluton of Mount Katahdin really comes around something like this. So in other words, this whole thing has been scoured out. The pluton used to just be a big dome that went around here. So, this is 5,000 feet here. Whether or not it was higher in this area at one point, I don't know. But we do think that the actual pluton of the Mount Katahdin Massif was not much higher than the summit is today. In other words, it might have been a couple 100 feet higher, because we know we see, I think it's granulite. There's a type of granite that we find that rims only in the upper sections, and because of that, you only find it at basically the contact between whatever the country rock that the pluton was put into as the pluton was injected in. In other words, the pluton went into a host rock, and because the host rock was cold, and the granite was very hot, you have a sort of a zone that's around the outside of it. Like imagine a ball, and then around that ball put a layer of skin around it, and the granite is slightly different. The chemistry of it and the mineral development is slightly different, and it forms kind of a layer around near the edge of the pluton, and you can find it all the way around it. And so we think, because we find it on the ridges near the top of this, that might have been the height of the actual pluton. But the pluton, all of this area was removed. This is a bowl, that's a bowl, and that's a bowl. And this is the famous, Katahdin Cirque right here. This is the Hamlin Peak Cirque. And these are just absolutely astonishing to see. They're just beautiful. Like, you wouldn't even believe you're in a Maine mountain. But snow piled up over this dome and basically drove across it like that. And as it did, it plucked away this side of it and this side of it. And eventually it found weaker areas. And as it did, snow just kind of kept piling on the mountain. And as it did, it created its own glacier. And the own glacier ended up flowing out this way, and out this way. And then all of these combined and started coming out this way. And as they did, they chewed away over time these bowls. Just like it started here, and then it kind of went like that, and then like that, and like that, and like that, and like that. And we know that these were glacially occupied outside of the continental glacier, because we find the terminal moraines right here. This is where the glaciers pushed stuff out and then halted, came back, pushed again, halted, came back, pushed again, halted. And when think of a glacier like a bulldozer. These are the snowbanks, but these snowbanks are made of rock and dirt as opposed to snow. So, anyway, that's Mount Katahdin, and it's an excellent example of a pluton that got scoured by glaciers, both continentals of the continental size and local glaciation. And that's what it looks like. So this right here is this right here. That right there is that right there. And so this dome used to go all the way over like this and out to here. It's probably egg-shaped, kind of like that. Goes down about another mile. It's about a mile. It's actually exactly a mile high. And glacial flow came this way up over and then plucked away on this side right here. And then you can see these moraines right here that are these right here. And it looks like, you can see it, looks like a snowplow came down and stopped and just left its tillings right here. So this is what we call a terminal moraine. And that's just from this mountain driving stuff down and pushing it. And this is as far as it went when it was a local, when it was, as opposed to a continental glacier, this was a localized glacier. Sea level change over the last 16,000 years. All right, so I always have a hard time with this, and I'm going to try to do it in a way that I can explain it clearly. And that's the hard part. That is the trick, right? So, as I said, this is the inundation zone. When the glacials melted and all the water went into the oceans and the glaciers receded, you have all this water, sea level's higher, Maine is depressed by about 300 feet. The water comes in and floods this area right here. So, what we do is imagine yourself standing at shoreline looking out into the ocean. That's the only way I can do this. And we're going to look back in time. As we go back, you're going to see sea level recede. At 2,000 years ago, it's probably about a quarter mile out, let's just say. And then at 4,000, it really starts to drop. At 6,000, it starts to drop very steeply. And then it sort of mellows out. And then it really plummets. At 10,000 years ago, sea level was down at about almost negative 60 feet. I think this is in feet, right? Not feet? Meters, 60 meters. All right, so that's 180 feet. Then sea level immediately will come right back up. It will come past where we were standing, and then it's going to go another 7 times 3 is 210, and it's going to go 210 feet higher than we are now. And this is sea level peak, and this is right after all the ice melted, and or at least the ice in this area melted, and the oceans flooded, and Maine is depressed. And then Maine ends up rebounding. And as Maine rebounds, water. All right, I got to start that over again. All right, we go out, sea level drops, it goes down to its base, and then you have the high stand at sea level. This was right after the glaciers melted. So sea level's high, and then of course Maine rebounds and sea level drops. And then sea level begins to continue to come up as more and more ice melts, and over time it eventually comes up to where we are today. Okay, that's how it works. Ice melted back here. Maine was hugely depressed right when it did, about 14 to 16,000 years ago. And so when it did, the sea flooded in, and this is when Maine is very heavily depressed. And then Maine begins to rebound, and water begins to recede, and then as it does, the sea level drops, and then sea level continues to rise until it finally comes back up to where we are today. And I'm fairly certain that is correct, and I'm going to double check that right now. Okay. I just wanted to confirm that, and I was on track. So, glacial maximum, what they're not showing in this is glacial maximum was 18,000 years ago, meaning that's as far as they got, that's as thick as it got, and that pressed Maine down about 300 feet. From 18,000 years ago to 16,000 years ago, a ton of water rushed in because the climate warmed very quickly at that time, and water rushed in between 18 and 16,000 years ago and flooded this area right here. So literally it was down, like you could think of sea level as being down here, but then it rushes way up, and then at 14 it begins to drop as Maine begins to rebound, And then at about 12, sea level is at its absolute lowest because most of the water, sea level is at its lowest because sea level is at its lowest because Maine has risen quicker than sea level could rise, and this is the inflection point. And we know that because we find walrus tusks and mammoth tusks out here in the Gulf of Maine, which was dry at that point. Not all of it, but the majority of the Gulf of Maine was pretty dry. It was a huge bay. And then sea level starts to catch up, and it begins to slowly fill back in. And as it does, it slowly climbs. First, it starts it very quickly, and then it sort of slows down and gets to where we are today. So in other words, the isosity of Maine rebounding ends up slowing down, and sea level catches up, and that's where we are today. So it's kind of confusing. Maximum sea level, maximum ice extent at 18, massive flooding between 18 and 16, sea level high. Sea level drops as Maine begins to rebound fairly quickly, and sea level has not yet had time to catch up. Then you reach a point where sea level starts to rise faster than Maine is rebounding, and we get an uptick in sea level, and then it sort of mellows off, and then it slowly creeps up into where we are today. So that's how it worked. Very confusing, but that's how it worked. Sea level inundation and retreat map. This is kind of cool. So this is what it looked like when sea level was at its lowest point. All of this area was exposed. So in other words, the Maine real estate or New England real estate was literally twice as big as you would see right now. These are interesting. These are basically terminal moraines that show the back and forth of seasonal fluctuations of ice in the Connecticut River Valley. Connecticut River Valley is a very deep area, big chasm through New England, and it makes sense that the glaciers would have come down and retreated, come down and retreated when they were melting. So in other words, it came down, stopped, came down, advanced again, stopped, retreated, came down, stopped, retreated, came down, stopped, retreated, came, and it did this in sections as it was melting away. And those are probably more or less seasonal. This is what the Gulf of Maine probably looked like at that time. You'd have an island here. You would have islands out here, islands here. The bay would be dry except for a very huge valley that is draining the rivers and everything from here. And so you would get something that would look like essentially just an inland small sea with a narrow channel, and then you would have small mountain ranges around the outside of it, which are of course now known as the banks. Out of water, these were all out of water. This extended probably down to here. If you went down 270 feet, that would put you at 100 meters would be 300. So yeah, you would have an area that kind of went like that. This would be so you'd have a pretty good size inland sea here with a narrow channel, maybe a small channel here, not nearly as defined as this, but you'd have a inland little sort of sea here, small mountain ranges here, some more small hills here, much bigger, and then this was all dry. Interesting what that must have looked like. Various landforms produced by the glaciation cycle. So glacier is retreating. Of course, you're not going to get these as it's advancing. You wouldn't be able to see them. This is the terminal moraine. It means this came down and then stopped and it receded, and then it came down one more time, and then there's a new moraine right here. You've got drumlins. These are just basically piles of dirt that are under the ice that always they kind of align in the same direction, parallel to the direction that the ice is moving. So if the ice is moving this way, the drumlins get stretched and dragged this way. Just imagine a clump of dirt in the ground and just stretch it out like that. In other words, just drag something over it and it's going to kind of stretch out, elongate like that. These were around, but now they're elongated. Erratic is just a giant boulder that got picked up from somewhere. You see them all over New England and then dropped. You get an outwash delta right here. So when these rivers, figure this has got tons of melting ice, lots of rivers. The rivers flow and then they push all this sand out and they make these deltas right here. These are all giant sand deposits. Think about it, everywhere you go in Maine, there's sand there's all sorts of sand pits. That's and if you notice, the sand is all very rounded too. And that's glacial water flooding into an area and depositing a ton of sand. I mean, when these things flooded, I'm telling you, they were absolutely colossal. Sometimes you'll have a dam that from the moraine will make a dam and it will back up and then flood out and then make a much bigger outwash. Kettle lakes, these are basically big chunks of ice that were in soft mud that melted and left a depression. So most of your small ponds in Maine, New Hampshire, Vermont, Mass, whatever, Connecticut, if they're not more than a few miles in diameter or whatever, and they generally tend to be more oval to round, it's usually a kettle lake, meaning a big piece of ice got dropped, left behind. It was so heavy it sunk in the mud, and then it depressed below the water table, and you get lakes. An esker is sort of the perpendicular version of the moraine. An esker is basically an elongated ridge of sand and glacial debris. It can form from a river running under the ice. It can be formed from a river running above the ice, and then depositing sand along in that ice channel. And then when it melts, you have a nice linear ridge, basically an upside down version of a river bottom, if you think about it. A came is essentially if I remember correct, a came is a area where there was a huge hole in the glacier and you had a large flowing river going across the ice and it was carrying debris and mud, and then it dropped and all that stuff. Let's basically imagine a waterfall coming over and just dumping into this hole, like there was a hole in here. And it dumps a bunch of sand and stuff. You get this pile of mud at the base of that waterfall. Again, it's like an inverted plunge pool, and that's what a came is. And you'll see it. They make these sort of roundish, dome-like piles. They're small hills. Usually in Maine, they're under 1,000 feet. But they're very conspicuous. They're rounded, and they're just domes of sand, and that's what a came is. A waterfall deposited those there. Marine facies produced during glaciation. Deltas are the glaciers up here. It's pushing sand and spreading it out and making these deltas. You have gravels and till down here that was made from the glacier plugging along and breaking apart pieces of this bedrock and making sand and gravels and stuff like that. You got some mud deposits right here in between the troughs of the deltas. In other words, once these once a layer of sand has come down and it stops, the sand stays close to the source, but of course the silt goes further distance and it will fill up these voids, sort of seaward from these delta deposits. So I have a moraine. This is where the glacier pushed and it stopped and it made a moraine. This cross section of one. You have a fan right here. This just could be another delta that went out here, but then for one reason or another got taken away, and so you just have the remnant of it. So in other words, if glacier comes back and pushes again, it will end up flopping this over and then eroding this, and you'll just have sort of a nub right here of what's left of it, and that's kind of what this is. This is what it looks like in real life. So when I look at this is what I see. Here is just sand that's fallen off of the top, so just disregard this. That's a shovel. And what you see here is you have, this is probably the most obvious one. I'll do this one first. This is, I don't know which way this came. I'm kind of thinking it came this way. So water came and flooded this area and deposited a bunch. It's like just taking sand and tossing it out with two hands, and it's spreading it laterally. And it makes sort of a fan that's like this. In other words, but this thing radiated out sort of, in 180 degrees. And then, and it probably was originally, it was like that. And then, for one reason or another, the fan stopped and another one came. And this time it flowed this way and made a whole new fan. And then one came this way, and then one came this way, one came this way, one came this way. And each one of these is an individual is an individual episode of flooding where sand gets blasted out and laid out into a delta. And these are just cross sections of different deltas. And these kind of overlap somewhat, but this is an interesting one that it goes in the opposite direction. So maybe flow was like this, and there was a cascade that went this way. I don't know. If it is a true delta and it came from the back, then they would be going. They would spread out laterally like that, which maybe that accounts for what this is. In any case, eventually the water receded, and the tops of these, I mean, these could have kept going further and further up, but whatever happened, and by the way, these are all underwater. Okay, these are underwater. They're not above water. This is above water. So what happened is the sea level dropped, and now the tops of this bank of this delta deposit, all these different ones, eroded and made a very flat deposit right here. So in other words, sea level was high. You know, the more I look at this, this could even be a all right, I'm going to come back to that. So just disregard down here. We're just looking at this area right here. Delta, sea level dropped, and you have erosion. And then the glacier advanced again and deposited. When I see rock, sand, gravels, this is a glacier that rolled along and eroded the top of this. Then sea level came back in and deposited a whole new set. You have muds right here, and then sea level dropped again slightly and deposited the sands again. And then up here, it looks like sea level dropped and the glaciers came back across over here. But what's really interesting is what's going on in here. You have a delta deposit, but you have a much more higher energy deposit. So what I think happened is you had a bunch of deltas that were put down here in a fairly high energy environment. In other words, sea level went in. You had some rounded clasts right here. This may have even been above sea level, and then this right here is when sea level came back up, and then you have some layers in here that these could be even delta deposits that just carried some rocks. You have a very large delta deposit right here that has a lot of different rounded rocks. This was either high energy, or this is an area where sea level dropped and you've got the glaciers came up. But this may actually be a river bottom. In other words, this whole thing might have been deposited, and then some sort of a river came through here and cut a channel that looks like this, and then it was filled again by sand deposits. But in any case, when you see sands, it was deposited in water. When you see a flat top, it was exposed to erosion. And when you see all the gravelly stuff right here, you know that this right here was when the glacier rolled across it again. I can't see this enough, but I'm guessing that sea level came back up, or this might be a carbonate deposit on top. Shallow water comes through, makes a carbonate deposit, and then gets deeper, and you start getting sands again. But anyways, this is very complex, but this is very common in deltas. You get sea level comes up, and sometimes you get higher energy environments, and then the rocks come in here. Sometimes it will drop, and it will cut into its own formations, and then you'll get a real nice, even. This is a very well sorted, not sorted, this is a I always mix those up. Just think of it this way. All this sand is relatively uniform in size, and this means that you had an area or a time where sea level stayed stable, and it was just depositing sand deposit after sand. Each one of these is a different episode of sand deposition. So very complex, but this is what you'll see when you go into pits in Maine, for sure. Seasonal terminal rains as ice retreated across Maine landscape. All right, so this is interesting. Think of the ice as coming down in this picture, and every year ice would advance a little, and this is when ice was melting. As a whole, ice was retreating, but winters are cold, summers are hot. We know that, and it was just like that then. So in the winter, you'd get an ice advance, and it would go advance. You know, I don't know what the scale of this is, but it's probably in the order, well, I don't know. I don't know. I can't tell. This is U.S. Route 1, but I don't know. Let's say that this is a quarter of them. All right. So maybe it may be in the order of 1,000 feet or so, or something like that. And the ice would go back and then advance, go back, advance, go back. And each one of these is recording those seasonal advance and back, advance and. But you know it. In other words, if it had advanced down, if we had a really heavy advance, it would have erased all these ticks. So we know that it was advancing and retracting, but it was always retracting further than it did advance, and it did this in a continued motion. That's why we know that this area represents a melting glacier, because we can see all the ridge lines of it advancing slightly and then going back. Because if it had decided to advance further, it would have erased all these. So and then you would have had to start over. But each one of these represents a seasonal fluctuation of ice and snow that pushes the glacier forward and then it retreats. Various glacial landforms right here. I don't know if you can see these, but these are striations on the rock. I don't know, you can't really see them here. You can really see them here. These shiny marks right here are literally gravels being scraped along the rock, and that's what you see right here. And they all go the same direction. That's from gravels getting ground across that. In other words, the glacier was grinding right on top of this. Oh yeah, you can see them right here. There's one right here, right here, right here, right here. So yeah, that's the ice. The glacial ice was physically right on this rock right here on the surface of it. You could touch that. This is in Wells, Maine. I believe all of these are. This is an erratic boulder that was just we know that, I mean, there's nothing else. I mean, here's another erratic right here. But this is a gigantic granitic boulder. And my guess is if you were to take a sample of that and do some geochemistry, you're going to probably find it comes from one of the plutons in Biddeford, or Webb Hannet. I mean, it could be brought as far away as freaking Canada. I mean, who knows? But chances are it's probably something within 100 miles, maybe even 20. This is near Crescent Beach in Wells, and Crescent Beach in the wintertime, the waves, because of the way they designed the seawalls, they didn't know any better. The seawalls in the wintertime take heavy-duty wave action, and they reflect the wave, and of course the wave ends up scouring the sand. And these are old tree stumps, about 2,000 years old. And what this is telling me is that sea level was lower because trees do not grow in the ocean. And this right here is what you would call a peat, or a clay hardpan. And it is also found with these. And the clay hardpan is essentially a bog or a swamp, and it's generally made in fresh water. And again, this is buried all summer long. You walk over it all the time, but then when the winter comes and you take the sand away, you find all sorts of chunks of this. And this is about 2,000 to 3,000 years old, and it represents a freshwater bog that was here at one time, probably at the same time these trees were here. And of course, this is back in the Wells Marsh, and man, there's tree stumps right there. Again, these did not grow in this area, so they grew at a time when the water was offshore. Glacial maximum at 16,000 years. Well, the glacial maximum is really 18,000 years, as it says right here. I'm going to change that right now. I'm not going to change it. It's just going to end up screwing up but glacial maximum 18,000 years. So just pretend that's an 8. I'll fix that at some point. In fact, I am going to do it. All right, I fixed it. Ta-da! 18,000 years ago, glacial maximum. You can see the glacial maximum also affected the southern hemisphere by extending off the continental shelf of Antarctica. Europe was heavily glaciated. Probably parts of Siberia. Of course, North America, Greenland, and then the ice froze, a good portion of the North Atlantic, and of course, Ogunquit and the beloved Marginal way right here under a ton of ice. Wow, present day, and here is, well, it's a little bit north, but Ogunquit's kind of like right there, but you get the idea. This is North America in her glory today. You got your Great Lakes. You've got, like, you can see almost the scrapes of glacial action as it scraped across the Canadian shield. You've got Greenland, Iceland. You've got Finland over here. I think Ireland, England over here. Alaska, the Rocky Mountains as we see them today. Puerto Rico here. Again, this is all getting yanked this way. And this is now pulling Pacific crust underneath this area and stretching it out over here. So that's what today looks like. We also, in this area back here, we have extension as this oceanic spreading center goes underneath and offshore of California. And then this it actually comes over and then goes back and under. I'm sorry, here the Cascades. or rather the subduction zone goes offshore and out here. But right here we have a subduction zone, and a part of this is going under uh, Washington and Oregon, and that's why we have the Cascade volcanoes right there. North America went over the spreading center, and that's so. In other words, spreading center on this side is going this way, spreading center on this side is going this way, and it's ripping off a ribbon of North America as it goes. And this will eventually go up through here and pull this right off. But if this continues to keep going, it may eventually completely subduct the spreading center, and then we're going to have much more volcanic activity over on the west coast. The White Mountains 300 million years ago. It's probably a good idea of what they looked like at 300 million years ago. 20,000 foot peaks, and believe me, you know, Washington itself is not the mountain that was there at 300 million years ago. You know, the highest part of it could have been anywhere. We are just seeing, you know, when you erode this whole thing, it's going to erode here first, and so you're probably going to end up eroding down here, or this is going to cave into here. Somewhere out here will be one of the higher parts that doesn't erode quite as fast. So, but when we look at it today, you can kind of get the idea. These once 20,000 foot mountains now look like this. So you just imagine everything under here has been eroded down, and you know, granted, you get some hard rocks up here for sure, but these mountains are compressing rocks that are way down underneath here, and making very dense, very difficult rocks to erode. And once you take off about 4 or 5 miles of this material, and we have, underneath is a reflection of this exact mountain range, but it's much deeper, and that's the root and the crustal root, and that's what you see here. These are all metamorphic rocks, and fairly high metamorphic rocks at that. And that's telling me that these are the roots that were once way deep under here. White Mountains today, 4,000 foot plus. Of course, Mount Washington at 6,000, and these over here are high fives, but this is unusual. It's only one area in New England where you get that high, and it's like that for a variety of reasons, and I may go into in the next couple of slides. All right, why are these mountains this high? Well, and how do we know it? It all comes down to metamorphic rocks. You can't make a metamorphic rock without applying heat and pressure. So, having said that, this is the direction of heat and pressure. In other words, the further you go up into this area, the more temperature and pressure you are slamming in, or you're exerting on these. So, since sterolite, or sillimanite rather, is one of the highest phase temperature and pressure metamorphic rocks, and we find it all through this area right here and here, well, one can summarize that this was probably the area of the highest mountains. And of course, the White Mountains are right here, but of course, all of these here, here, and here were also very high pressure, which means 20 to 25,000 foot peaks probably occupied this area right here. These out here were the adjacent foothills of it, probably in the order of 20 to 15,000, and then as you go westward, they would get lower. And of course, as you went eastward, you would be going into also very high metamorphic rocks, because Avalonia was connected here. The land went out to here somewhere, and then of course Africa finally shows up. But you would have had a coastline that's out here, and these mountain range, probably the mountain core was something like something in the order of like this. And so that's how we know that these mountains were at least 20 to 25,000 foot high, because here's the core, and the highest temperature and pressure are right here. So we know that these were the highest peaks. And this explains it even better. So think of it this way: slate, phyllite, schist, gneiss, migmatite. You have some melting right here. And believe it or not, most of the mountains in New England are from volcanic arcs. So as this arc slammed into, think of this as the Atlantic, and then this is, you know, Vermont or New York, and this is subducting under North America. The more you build these mountains, the more pressure gets exerted, and the more temperature gets exerted in this area. So this area right here was represented by this area in here, and we've just removed everything. So increasing temperature pressure change rocks as it heats up, and this really shows it. So remember this? Notice it's almost like you have the same colors on each side. Well, That's exactly what this is. This was the mountain range of the White Mountains when it was originally built. And up top we had low metamorphic rocks, and then we had higher ones as you went into the depth. Granulate, that was one I was looking for. So, and this also probably explains what's going around, partially what's going on with the uplift of the Appalachian Mountains. So, over time, these all get eroded. In fact, they get eroded down to somewhere in here. So let's just say that's 6 miles of material. What we see right now of the White Mountains is a line that's here. And so when you get into that area of central New England, you're looking at the silmonite. And that silmonite is the core of a very giant mountain range. And of course, as you go out, your metamorphic intensity gets lighter. So we'll go back. This right here is this right here in this dead center. And then this out here is this out here and this out here. So it's really simple. Now, when you take all this, so when you have all this material on top, you're pressing down the root. And as the root goes down, it heats up into the mantle. It gets pressed into the mantle. When you take this off, this pushes back up and actually domes these right here. And that's why this becomes more steep. And that accounts for why you see this such a steep area right here. This was probably much flatter at one time, but it's now been domed up. And that's from isostatic rebound right here. So once you take all this material off, there's not as much weight to press down, and then the mantle pushes back and then basically domes the area right here back up. And that's what we're seeing. And you combine this with slab breakoff, and then of course the erosion makes the things lighter. There's a variety of reasons why in the last 30 million years that the Appalachians have begun to rebound, because they were in fact a gigantic mountain range, and there's plenty of mountains still left underneath, and we're starting to see the cores of the mountains, and that's what the White Mountains are. In fact, most of the Appalachians are just this. You go in anywhere in the Appalachians in the center, and you're going to find high pressure minerals. And this is a better way to explain it. White Mountains, New England Mountains, Appalachians in their heyday, very heavy, pushing down from the lithosphere to the ionosphere. Erosion takes all of this away, spreads it out. This actually starts to stretch a little bit. And guess what? Once you've taken the weight off and this begins to stretch and bow, you're going to get something that lifts up. And that is a very, very good idea of what's happened, at least without a doubt, a piece of the puzzle of what's happening with the Appalachian Mountains around 35 million years ago. You're definitely getting some sort of an uplift from isostatic rebound. So large young mountains push down on crust, removal of, and then over time, removal, erosion of rock material lightens them, and then the crust rebounds to lack of weight. This is one of the three key principles that would help lift the Appalachians in the last 60 million years or so. A slab breakoff, erosion, and then isostatic rebound. All of these would contribute. And now, not to mention, you're heating up the root. When this root bounces, even though it's 1100 degrees, because of this pressure, it's not going to melt. But when you pull this root up, and you don't have that pressure to keep the root from melting, you're going to get melting down here. And when this happens, this is why after orogenies, you're always going to get these post-orogenic plutons, and you get massive amounts of granites that stitch these island arcs to the continents, because after the initial collision and the mountains push up 20,000 feet, and they also push down a lot, they push miles into the mantle. Once you remove that material, that root stays hot, but it's no longer got the pressure to keep it from melting, and then it begins to melt. And that's part of it's almost as if the root erodes. And then you get granitic plutons like Sebago Lake, like the Wildcat granite, the Peabody granite. You have the Oliverian Dome on the northwest side of the White Mountains. All of those are post-orogenic, meaning that when those mountains began to erode, or the slab started dipping, you got material that heated up and injected and basically forced its way up through through both isostatic rebound and slab breakoff and slab descending into the mantle. When the slab descends in the mantle, any one of those can induce post-orogenic melting. You also get it while it's occurring, but you definitely get a series of felsic granitic melts after the mountain building episode has finished, and the mountains begin to actually begin to collapse on themselves, because if they're big enough, the weight of them alone will force them to start to depress, because you no longer have the compression holding everything up. And that's, of course, represented here. Here's another isostatic example. You got mountain, you've got displacement in the upper mantle, lithosphere, whatever. And then as this begins to erode and relax, what happens is this begins to push up. And as it does, it starts to stretch this. And it also allows plutons to get injected in here. And then as it erodes further and further, you actually get to see the plutons at the surface. And that's why when you drive through New Hampshire and Maine and what have you, you begin to see all sorts of granites, because these were emplaced during the mountain building episode and soon thereafter. So of course this material ends up getting dumped out here, and believe it or not, you start to actually get weight of this set, because you can't take the weight away, it needs to go somewhere. And as it piles up out onto the crust, it begins to actually downbow the crust. And you're starting to see, as it downbows here, it helps actually flux here. So if something goes down, it has to bow up in other places. And so a lot of times it will start to bow up the mountain range and of course offshore. And you can see, you can almost get some faulting in here from that. And this is the one that tells the true story. Where are the sediments from the 20 to 25,000 foot Appalachian Mountains? Where are they? Well, they are here. Here, 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 really in here. When these mountains erode, and notice, this is thickness of sediments. There's hardly any sediments, less than, not more than a couple 100 feet at the most of sediments right here. But my God, look at all the shedding. 14 to 16 kilometers of sediments have been deposited offshore. And that's all that is the Appalachian Mountains eroding. Huge clastic wedges back here, and a lot of this material that went here, and ended up in here. And that's why the Gulf of Mexico, the Gulf of Mexico is a modern day gigantic basin that may or may not actually fill up with sediments. And if it does, it's going to continually push down as it does. So the Gulf of Mexico is currently filling with sediments. And if you notice, you don't see nearly the amount of sediments over here from the Rockies, because the Rockies are younger, they have not eroded as much, and yeah, you've got some sediments out here for sure, right? You can see them. You can see them here, but you don't have anything like you have out here. And that's because these mountains are, 3 times as old. They were much higher, and they've they've had more time to shed all their weight out here. And you can see basically this whole area is Appalachian sediments being deposited. And the Rocky Mountains, they just don't even compare yet. They just haven't shed enough stuff. Now, granted, it's out here, but not like it. And this probably would be much thicker up in here. Like this here would go along way up here and out in here, but it's all been scraped away by glaciation and deposited off here. Gravity map. Forgot about this one. All right, so the gravity map, it kind of tells you what kind of crust you have underneath you, if you can read it correctly. And sometimes it's hard even for me. But what it's telling me is that blue is heavier, older, and of course young. Pink and purple are younger and warmer. And that actually makes perfect sense if you think about it. Out here is younger, warmer, not nearly as thick, so it's not nearly as dense. So therefore, when they do the gravity anomaly, when they chart the gravity, it moves much slower through here, indicating warmer crust. Then with cold brittle crust, when you do gravity measurements, it moves much quicker. So that's why we know. And of course, back here is the Grenville. This is a Grenville area, which is much more dense than any of the Appalachian mountains. And so, of course, it's a heavy, deep blue, much colder, much more brittle, much deeper. The orange, I mean the purple and the pink right here, this is associated with the rift zone of the opening of the Atlantic Ocean, and it was filled by basaltic rock, which was unmetamorphosed and not dense. Because it has not been compressed, it is not dense, and therefore it does the P waves do not travel through it as quickly. So it shows up as warmer and less dense crust. The White Mountains are right in here. So of course they get a fairly good divot in here, and that's because the underneath the White Mountains is a crustal root that's been very dense and packed, and so that's why you get that. And of course, it's hard to see, but you get a line of them going right here, and then another line right here, and that's because these are deep-seated roots right here. I think this is the gabbro of Sugarloaf and the Saddleback. There's a huge pluton up here. Pluton back here. The Katahdin one doesn't show up because it is rhyolite, and the rhyolite was never metamorphosed after it was injected. If it was very lightly, so therefore the rhyolite is not that dense. It is lighter, and so therefore you are not getting a deeper or a thicker or colder reading. The reason why this out here is showing a warmer crust, again, the moho is higher. And of course, you don't have the mountains out here. The mountains were over here. This out here is basically crust that was left behind as Africa split, and there just isn't a lot of relief, so the crust isn't nearly as thick. It's not as dense, and so therefore you have a lighter light gravity. So heavy where it's old and thick, and where it's old and thick, or just old or thick, you get blue. Where it's thinner and younger, you get reds. And that's, of course, here. We know that, of course, the coastline, the ocean has, this is down by, 600 feet or so. And then over here, you have a mile of rock on top of the continent. And so that's why you have blue. This out here just has less rock, therefore less gravity pulling down. This right here is an interesting one. I'm going to say that this is part of Avalonia right here. And Avalonia is heavily granitic. So therefore, even though it's very dense, and this is a very dense part of Avalonia right here, it's not a mafic, so it doesn't have the necessarily the density nor the weight to give you a heavy-duty gravity anomaly. And just to rehash what I had gone through, the depth and the temperature of the crust, this is clearly showing you what this is. Dense, not as dense cold, not as dense and as cold. And you can see that right here. That's the suture zone. We went through this. These are the terrains right here. Avalonia, Gandaria. You've got the arcs right here of the Taconian orogeny, of course, North America. And we think that part of this had to do with slab breakoff. So the moho on this area is higher. Of course it is, because this crust right here was derived from someplace else. It was rifted off of Africa and Amazonia. It is much lighter. It is composed of a lot of island arcs and sedimentary stuff. The roots are not that deep, not until you get to true North American crust, which is much deeper, much thicker, much heavier, and of course the moho is much further down. And possibly this might be higher up, we don't know. But maybe it's also the result of possible slab breakoff, as indicated here. If the slab truly broke off right in here, then all this weight that was pulling this down would now rebound, and you might get the moho might have rebounded. So I'm just trying to pull these both into it. And of course, you add the erosion of the mountains; they make them lighter. They are also going to rejuvenate. Magnetic map of Maine. This is showing some of the arcs, which is cool. Arcs are indicative of mafic volcanics, sometimes intermediate volcanics, but in any case, iron is usually associated with at least some of the arcs. And when you have a good arc and you have some mafic lavas, you have iron. And this is an arc. This is an arc. this is an arc. This is actually probably related also to faulting. Um, you've got some interesting stuff here. Why is that so magnetic? I don't know why these are magnetic, but anyways, magnetics are usually associated with mafic rock, meaning it's iron rich. This is the coastal volcanic zone. This is a huge area. It's Falmouth, Brunswick volcanic area here. This is an area of lots of volcanics and lots of mafic. There are some mafic volcanics and plutonic activity in here. So that's why you're getting a high magnetic. Magnetics may be associated with the Nuremberg fault, but maybe also, I don't think it could be part. If this slammed in, it would have made some sort of an arc maybe. This is the Maine, the trough of central Maine with all your slates and everything. This is the Ganderia terrain. A lot of sediments derived from island arcs and just a melange of felsics and mafics that made deposition from eroding island arcs that made the central Maine slate belt. You've got arcs up in here, arcs up in here. These are probably more associated with the tectonic orogeny. This might be more Acadian. And of course, right in here, Sugarloaf is right in here, and I think it's right here. And what's interesting is Sugarloaf is a gabbro. A gabbro is a mafic igneous rock. It's like a granite felsic, but gabbro is the mafic version. They're not as common. And Sugarloaf is a gigantic gabbro intrusion, and it shows up right there. You know, Saddleback would be over here, Mount Abraham here, what have you. So, and you can see the line. The lines line up. This has just got wedged, just pancaked in like that. Just a quick review of how the arcs came. I'm not going to go through this, but this was just the tectonic events of North America when it was forming, and of course this was the Canadian shield right here, made up of craton of cratonic bits. You got the Superior, the Slave Ray, and of course the Wyoming craton. And about 1.8 billion years ago, you had a series of the first when these came together, you made the trans-Hudson orogeny. But when the trans-Hudson orogeny stopped, you had a series of arcs that made the Yavapai and the Mazatol. Then you had the granite rhyolite. Basically, you had a long period of time where a lot of subduction was going on the southeastern side of North America, and they're just represented by these cross-section diagrams right here. This was the slab going down to make the trans-Hudson. The slab went down, of course, slab broke off, and that's what it looks like when a slab breaks off. This right here is essentially showing trans-Hudson slab break off, and then the Yavapai, the Mazatol, the granite rhyolite, and the Grenville. These are just trains that just got slammed onto here and eventually accreted to make up southeastern North America. And of course, it gets more complex, where we have the Grenville orogeny, and then finally the Appalachians, and of course you have subduction coming in from the west with the Farallon plate. And so eventually, this is the cross section. It went from this, a very simple diagram with two pieces of cratonic materials that ended up coming together to make the first more or less supercontinent, or the North American craton rather, to this that has. This was the original North American craton with the Slave Ray, Wyoming, and Superior. And then you had the mid-continental rift where it tried to break up. And then you have the Yavapai, Mazatol, granite rhyolite, Grenville, and of course, finally, the Appalachians. And of course, also in the Cenozoic, you have the Cordilleran right here of the Rockies. And that's indicated by the Farallon plate diving under here. So, suture zone, suture zone, suture zone, suture zone, suture zone, suture zone. And then, of course, you have the Appalachians with its final subduction going underneath North America. And if this breaks off, which I'm making a case for, it's going to rebound this area right here. And finally, the tectonic terrains of New England. So all of these, or rather just this area right here, is represented by all of this right here. And North America, this is the Grenville, the Adirondack Mountains right here. This is the Laurentian. Basically, this is all North America. This is the Grenville orogeny right here. Pieces of the Grenville, outliers. They were pulled out when the Iapetus Ocean opened up. You have the tectonic orogeny with the Bronson Hill right here terrain. Then you have the island arc of the, I forget if it's Roe and then Bronson Hill, but anyways, these are two island arcs right here associated with the tectonic orogeny, and in between that you have basically the Tectonic Sea, actually it might have been over here, I forget, but there's a little seaway that might have been in here, and then you have the Ganderia terrain right in here, which is made up of sedimentary rocks from various island arcs on their way over. And then, of course, you have the coastal volcanic belt, and then Avalonia is here in red, which is a ribbon of continental crust off of Africa. This in here are bits and pieces from probably Amazonia to make up the Ganderia terrain. And then over here is something we call Meguma, and Meguma is something else. It may even be from Eastern Africa. It's very far away. We're not really sure. Yeah, the Moortown terrain, that's associated with the tectonics, and then the Ganderia is in here. Yeah, that's all Ganderia terrain. So tectonic, Akkadian did this, and then eventually Africa shows up. And this is just another picture showing what in more detail. Oh, by the way, these are post-orogenic plutons. This is actually something much different right here. This is maybe associated with the New England hotspot. But this is the Sebago Lake Pluton. You got the Katahdin rhyolite somewhere in here. So yeah, marginal way, Iapetus ocean sediments, Avalonia, Iapetus ocean sediments. You've got the tectonic area right here. You've got island arcs here, here, and here. Of course, they get older as you go southeastward. And you have the Grenville. So Grenville terrain here at 1.25 to 0.9. You could say 1,250 to 900 million years ago. You have the tectonic at about 480 to 440 million years ago. And then you have the Akkadian orogeny, which closes the Iapetus Ocean and adheres the Ganderia and the Avalonia terrain from about 400 to about 380 to 360 million years ago during the Akkadian orogeny, and then eventually Africa shows up around 300, and that's the closing of the Iapetus of the Rheic Ocean, because behind Avalonia is an ocean called the Rheic, and when that finally shuts, we have Pangaea. So just a quick word about metal forming zones. Metals have a tendency to form in a variety of settings. Generally, back arc basins do well. You can have it in rifting areas. But the point being is that you need magma to basically work its way to the surface. And it can't be just any magma. It needs to be magma that's derived from oceanic crust being subducted. When it goes down and melts, it throws water in, and then it creates volatiles. And then these, in a nutshell, pond and magma chambers underneath here, each one of these is a magma chamber. And then depending on what type of magma chamber and where it is and all these other things, you're going to start extracting minerals like gold, nickel, palladium, platinum, copper, all of those, silver. And you really need, these seeds are in the magmas, but you need the right environmental conditions to get these things to form. And so the reason I'm showing this is because if you look at where they are in Maine, you're going to notice that they're in back arc areas when this was subducting, and they're in areas where rifts were. And so I'm going to show that. So slab going down, melting, sending up volatile rich, melts, and they're getting lodged into the crust, so they're interacting with that. And of course, these reactions are going to start producing ores. So where do they usually form? So we got slab going down, you've got some continental crust right here that it's mixing with, you've got some arc-related crust right here, then you have continental crust back here. So this is probably juvenile crust being being sutured to more mature crust. So, and then as juvenile crust juvenile crust is usually associated with island arcs. So it's new crust, it's young, it gets thrown up onto old crust, which is mature, which is more felsic, and when you have interactions between these two, plus real mafic oceanic crust glunder, that's when you get the right environments for ore metals that can be mined. So there's a lot going on in here. I'm not going to go into in great detail, but if you look, this would be possible back arc. This would be possible back arc. There is rifting down here. There is maybe some rifting in here. And we're going to see if that lines up. And as it turns out, it sort of does. So you got sandstones and stuff like that, not that heavily metamorphosed. You've got volcanics down here. And then, of course, you have the sedimentary deposits of the Gandaria terrain. And you have mines in these. So this is located on an island arc, sort of near Sugarloaf, which is gabbroic, and it's an island arc, and it's associated with some volcanics that were probably above it. And of course, yep, we got a mine. Katahdin, next to the rhyolite, the pluton. There's a huge pluton that came in here, mixing with juvenile crust, and probably an underlying of Grenville crust, which is mature. And of course, you get volcanics, you have a mine. Here, these are all mines associated in the island arc areas. And then here, you've got volcanic rocks in this area, and of course mines. Now, right here we have just pure sedimentary with not much back arcing or anything like that. You don't really have a lot of ore metals. However, you do have other minerals that are regenerated around these plutons. This is the Sebago pluton in here. This down here, oh, this is limestones. So these limestones, so some of the calcium carbonate is reacting with some of these volcanics and granitic injections to make other with minerals. Yeah, we know because there's tourmalines up in here. There's definitely some minerals down in here and in this area. So Maine's kind of loaded with it, but a lot of the ores you kind of are going to associate with either back arc areas or island arcs. And yep, this is an island arc, and this is an island arc, and you've got your mines kind of lined up right along that. This is the present day global view. I don't really need to go into it in great detail. Antarctica has a glacier, in case you're wondering. I hope that's not news to you. Greenland has one as well. You've got the Indian Ocean being subducted under Southeast Asia. When I say the Gandaria terrain, this area right here, it is very closely related to what this area is right in here, and possibly this. All this right here is just arcs and sediments being deposited, and eventually this is going to smash in, and it's going to make something like Gandaria. So it's got some, subcontinental crust. It's got some sediments. It's got some island arcs. Just a melange of all sorts of stuff on the northern side of Australia is eventually going to be a Gandaria terrain. Subduction of the Pacific Ocean going underneath Asia. Africa is splitting apart. The very remaining last parts of the Tethys are being subducted under Turkey in the Mediterranean. You've got the Caribbean here, North America. You got your passive continental shelf, and that's the world as we see it today. So in 50 million years, what can we expect? Well, we know we've got subduction here. We know this is going this way, this is going this way, this is going this way, and this is going this way. This piece right here is going to get dragged out here. This piece here is going to get dragged this way. I don't know what this is going to do. I know that this is going to slowly get subducted under here. So let's see. Africa is probably going to go this way, and the mountain range is going to start to really build right around here. All right, so 50 million years ago, North America has pushed much further northwestward. I would say that we are probably in the latitude of northern Labrador at this point. Very, very cold if the conditions are the same. Here's the mid-ocean ridge. The Atlantic Ocean is much wider. Africa has now merged and slammed into Europe. So there's no Mediterranean. There's Mediterranean mountains. India has continually pushed and probably stopped at this point, and the Himalayan mountains are starting to erode. They may already have. Subduction is going to continue, and you're going to have a massive mountain range probably over here. Baja California has been sucked up and under Alaska, or it's about to. Antarctica is rotating, and it's starting to move northward. Australia is essentially, it's a little bit further south, and that's because the subduction zone is opened up on the western side of it and is pulling it towards the south now. The Indian Ocean is beginning to close, and the Atlantic Ocean is king. Of note, where the Puerto Rico Trench is right here has started to move forward, and there's actually a continuous trench now on the eastern side of South America. There's also a trench over here on North America that is starting to subduct under North America, the Atlantic Ocean under North America. I am not 100% sure I agree with this. We are now noticing that these subduction zones that just mysteriously pop up out of nowhere are nowhere found on Earth today. And we think that that's not how, I mean, it made sense that, all right, you pile all this material out here, eventually the ocean slab, the ocean crust is really old, it's cold, it's going to eventually start to sag, and maybe it will snap, and maybe it does in some places. But more likely, it's these transform faults along these ridges that start to create subduction. And it makes sense that this might wrap around, and it makes sense it might start to move up here. But whether or not it's related to this, we don't know. But I'm not 100% agreement that it just shows up like that. So anyway, mountain range here. Japan gets welded on to Asia. And then, as I said, this is going to all create a gigantic. See, there's mountain range right here. Indonesia has rotated clockwise and is now going to be part of Asia, or Eurasia. 150 million years from now, Africa has pushed much further north. It's approaching the Arctic Circle, the northern part of it. It's rotating Asia in a clockwise direction. The Pacific Ocean, I'm not sure if this is depicted as closing, as it still looks fairly wide. However, the subduction zone that was on the eastern part has now been subducted under North America. The mid-ocean ridge is now getting sucked under North America, and it's eventually going to go under the Appalachians or whatever is there now, probably something new. Subduction has now gone further up under Greenland. Subduction continues, basically closing what is now known as the Indo-Atlantic Ocean. And so this is going to go this way, this is going to go this way, this is going to disappear, and you're going to get a new mountain range in here. And then this is going to shut, and this may close here, this may bash into here, I don't know. But in any case, I mean, if you have two subduction zones on each side, there is almost a possibility it could separate and split the continent. But I doubt it because it's made it this far. So, but the closing of the Indian and the Atlantic Oceans is now happening, which means the Pacific would be expanding. So, all right. And at 250 million years from now, the Pacific Ocean, or the Pacific, Neo-Pacific Ocean maybe, is gigantic. There's just one big giant subduction zone on the west side of North and South America. Australia and Antarctica collided, making a colossal mountain range. And this is called Pangea Noir, the next Pangea. Mediterranean mountains are gigantic. They run up through what was Mediterranean, Eastern Africa. And of course, the Appalachians, or the new mountains between the southern part of Africa. New England collided with this part of Africa during Pangea, but now it's collided with the bottom part of Africa for whatever you want to call the new supercontinent will be in about 250 million years, when the Atlantic Ocean closes and the Indian Ocean closes. And there's Belly, and that is the end. And I am very glad to get this done because I've wanted to start on something else. And my new one is going to be evolution of Hawaiian volcanoes, and I'll probably do each island in detail. So keep an eye out for that. It's going to take me a while because I have to start from scratch on that and put slides together. So thank you so much for watching this series. I hope you have a great year. Happy New Year, right? It's a little late for that, but it is the new year. And aloha, and thank you for watching.